Look at the world around you, the solid desk beneath your hands, the light streaming through the window. It all feels undeniably real, permanent, and fixed. We operate under the deep intuitive assumption that the universe exists exactly as it is, whether we are looking at it or not. But what if this assumption is the greatest illusion ever constructed? What if reality as we know it is not a continuous physical stage, but rather a fluid tapestry of mere possibilities? Welcome to the most profound, unsettling mystery in all of modern science. In the realm of quantum mechanics, there exists an experiment so simple in its design, yet so terrifying in its implications, that it threatens to unravel our very understanding of existence. It is called the double slit experiment. At its core, this experiment points to a truth that sounds more like science fiction than physics. Matter might only decide to exist in a solid state when it is being observed. Imagine a video game. To save computational power, the game's engine only renders the graphics, the trees, the mountains, the enemies, when the player turns their digital camera to look at them. When you look away, that highly detailed world dissolves back into lines of code, existing only as mathematical potential. For over a century, physicists have been forced to confront the terrifying possibility that our universe operates on exactly this same principle. To understand how we discovered this glitch in the matrix of reality, we must travel back over 200 years. The year is 1801 in Georgian London. Inside a heavy velvet curtained study, the air is thick with dust, illuminated by a solitary razor-thin needle of sunlight piercing through a tiny pinhole in a wooden window shutter. Here, polymath Thomas Young, a physician and Egyptologist who helped decipher the Rosetta Stone, is about to challenge the posthumous godhood of Isaac Newton. Newton had famously declared that light was made of corpuscles, tiny solid particles. But Young, driven by an artistic obsession with harmonies and sound waves from his medical studies of the human voice, suspected otherwise. Taking a crude slip of cardboard, Young split that single beam of sunlight. If light were purely particles, he should have seen two distinct lines of light on the opposite wall. Instead, he watched in awe as concentric rings of light shimmered and overlapped, creating a distinct interference pattern of alternating bright and dark bands. The pattern proved undeniably that light travels as a wave. Young sketched these intersecting arcs of light in faded ink on textured paper, a drawing that survives today as a testament to his genius. But his discovery was met with fierce hostility. A vicious, anonymous smear campaign in the Edinburgh Review, spearheaded by Henry Brotham, mercilessly mocked Young for daring to contradict Newton. The public attacks were so severe that Young's book sales plummeted, and he essentially abandoned optical physics in despair. Yet his simple tabletop demonstration had drawn the very first map of a labyrinth that would eventually consume physics.
More than a century later, the scientific landscape had transformed, and Young's wave theory of light was under siege by a new generation of titans. By the 1920s, Albert Einstein had resurrected the particle theory of light through the photoelectric effect, introducing the concept of wave-particle duality. The ultimate intellectual showdown occurred in October 1927 at the 5th Solvay Conference in Brussels. Inside the opulent Belle Epoque dining room of the Hotel Metropole, rain lashed against high-arched windows. The air hung heavy with the pungent smoke of Einstein's pipe and Niels Bohr's cigars. The formal photograph of that gathering shows 29 men and 1 woman, Marie Curie, in starched collars and waistcoats, the greatest assembly of minds in history. They were warring over a shocking new hypothesis. If light waves could act like solid particles, could solid matter, like electrons, act like fluid waves? The answer, proven accidentally by the Davison-Jumor experiment bouncing electrons off nickel crystals, was an emphatic yes. The quantum realm was born, bringing with it a profound crisis. Einstein, a strict realist deeply disturbed by this loss of determinism, aggressively argued for hidden variables. He believed the universe existed independently of our observation. But Niels Bohr championed the Copenhagen interpretation, adopting a pragmatic, almost philosophical stance. Bohr insisted that asking what a particle is doing before you look at it is fundamentally a meaningless question. A particle doesn't have a defined location until it interacts with an observer. The battle lines for reality were permanently drawn.
The theoretical debates of Solvay were abstract, but as technology advanced, the double slit experiment evolved into a physical nightmare for objective reality. In 1961, Klaus Jonsson successfully performed the experiment using actual physical electrons instead of light. But the true paradigm shift arrived in 1974 when Italian physicists Pier Giorgio Merli, Gianfranco Misiroli, and Giulio Pozzi managed to fire single electrons through a double-slit apparatus, one at a time. Imagine firing a tennis ball at a wall with 2 doors. It must go through one or the other. But in the quantum realm, the rules of logic disintegrate. As single electrons were fired, the detector screen initially showed a seemingly random scattering of white dots against a black void. However, as thousands of these individual dots accumulated, they didn't form 2 bands behind the slits. They magically self-organized into distinct, unmistakable vertical fringes, an interference pattern. Even when fired completely alone, a single particle of solid matter somehow acts like a wave, passing through both slits simultaneously, interfering with itself, and only deciding where to land at the exact moment it hits the screen. The particle exists in a superposition, a ghostly statistical wave of all possible locations. It is everywhere and nowhere at once, waiting in a mathematical limbo. But the most chilling discovery was yet to come. When scientists placed detectors at the slits to secretly watch which path the electron actually took, the wave function collapsed instantly. The interference pattern vanished. Watched matter simply behaves differently. The act of measurement itself forces the universe to choose a definite state. But how far does this strange rule extend? In 1999, at the University of Vienna, Anton Zeilinger's team pushed the boundaries of the macro world. In a sterile, temperature-controlled basement lab smelling of ozone, they fired Buckminster fullerenes, massive soccer ball-shaped molecules made of 60 carbon atoms, through a diffraction grating. Even these giant objects behaved as waves of possibility until measured. But the true blow to our understanding of time and space came with the quantum eraser experiment, validating the delayed choice theory proposed by John Archibald Wheeler. In this mind-bending setup, scientists measured which slit a particle went through, successfully collapsing the wave function and destroying the interference pattern. But then, before any human could actually look at the data, they completely erased the measurement from the computer's hard drive. Astonishingly, the wave pattern instantly returned to the screen. By deleting the information in the present, they altered how the particle behaved in the past. The universe seemingly knew the data was deleted. The glowing, nebulous blue cloud of probability waves only converges instantly into a sharp, solid, glowing sphere when an artificial eye retains its gaze. If the record of the observation is destroyed, the universe simply unrenders the event, returning it to a state of hazy potential. This experiment fundamentally shatters our linear perception of time, suggesting that choices we make today can literally reach backward and rewrite the physical history of the universe. is an observer. Nobel laureate Eugene Wigner took this to its philosophical extreme, proposing that human consciousness itself is the sole catalyst that collapses the wave function. Without a conscious mind to perceive it, the universe remains in a state of suspended animation. While mainstream physics prefers decoherence theory, where any physical interaction, like a stray gas molecule or a camera lens, counts as an observer, the eerie parallels to modern technology remain impossible to ignore. Today, technologists argue that the double-slit experiment is the ultimate proof that we are living inside a highly advanced holographic simulation. Just as a video game engine optimizes memory by rendering graphics only when the player looks, our universe might be an information processing substrate that only renders solid matter upon measurement. John Archibald Wheeler called this the participatory universe, famously declaring, "It from bit." We are not merely passive bystanders in a pre-existing cosmos. The very act of us looking, measuring, and interacting with the world is what causes the universe to materialize. The unobserved universe is not an empty room. It is a room filled with swirling, infinite mathematical probabilities waiting for a question to be asked. Reality, as we experience it, is a collaborative effort between the cosmos and the observer. As you sit there, listening to these words, touching the desk in front of you, remember, it is only solid because you are there to feel it. You are the architect of your own reality.